Hello everyone, welcome back to my channel Orbit Unknown. Today we are fascinating the very interesting story about K2-18b, the ocean. World that changed everything. Part 1. The discovery 124 light-years from Earth. In the constellation Leo, there is a world that scientists believe could be harboring life right now. It orbits a star smaller than our Sun, in a region where water can exist as liquid. Its atmosphere contains chemicals that, on Earth, are produced exclusively by living organisms. And for the first time in human history, we are searching for signals of intelligent technology on its surface. This is K2-18b, and the discoveries surrounding it are forcing us to completely rethink what we believe about the universe and our place in it. For thousands of years, humanity asked a single question: are we alone? We built telescopes. We sent radio signals into the darkness. We named an entire scientific discipline, the search for extraterrestrial intelligence, or SETI, dedicated to finding an answer. But most of those searches were theoretical, educated guesses based on planets we'd never actually seen. Then something changed. In 2024, astronomers made a discovery so profound that it rewrote the textbooks. They found a rocky world, smaller than Neptune but larger than Earth, orbiting in the habitable zone of a distant star. An atmosphere rich in carbon dioxide, methane, and possibly something else, something that moves the needle from possibility to probability. And just this year, in July 2026, scientists pointed the most powerful radio telescopes on the planet at K2-18b, scanning for artificial transmissions from a civilization we've never met. What they found, or didn't find, is transforming our understanding of the search for life beyond Earth. This is the story of that world, the science behind it, and the profound implications of what we've learned. Part 2. To understand how revolutionary K2-18b truly is, we need to step back to the beginning of the search for worlds beyond our solar system. For most of human history, the existence of planets orbiting other stars was pure speculation. Philosophers debated it. Scientists theorized about it, but we had no way to prove it. The stars were too distant, too bright. Any planets orbiting them would be invisible against their stellar glare, like trying to spot a firefly next to a searchlight. That all changed in 1992. An astronomer named Alexander Wolszczyn discovered the first exoplanet using an ingenious technique, listening to a pulsar's radio signals and detecting the tiny wobble caused by a planet's gravity. Suddenly, the universe was full of worlds. But these were lonely discoveries, distant, unknown, often hostile. Gas giants circling close to their stars. Planets in regions where water boils away. Worlds that seemed fundamentally hostile to the kind of life we know. The search for a truly habitable world, a place where life could theoretically exist, became the holy grail of astronomy. Scientists defined a concept called the habitable zone, the region around a star where a planet receives just enough heat that water can remain liquid, not scorched by stellar radiation, not frozen distant cold, the Goldilocks zone. And then came the Kepler Space Telescope. Launched in 2009, Kepler revolutionized exoplanet hunting. It stared at the same region of the sky for years, watching for tiny dips in starlight as planets passed in front of their stars. The resulting haul was staggering. Thousands of new worlds. Many of them in the habitable zone. Many of them Earth-sized or super-Earth-sized. Scientists like Niku Madhusudhan at the University of Cambridge began asking a dangerous question. What if the habitable zone isn't limited to Earth-like worlds? What if we've been too narrow in our thinking? And then they looked at K2-18b. Part 3. K2-18b was discovered in 2015 by the Kepler Space Telescope's K2 mission. At first, it seemed unremarkable. A sub-Neptune, bigger than Earth but smaller than Neptune, orbiting a red dwarf star, one of the most common types of star in the galaxy. But the location told a different story. Its host star, K2-18, is a dim red dwarf about 122 light-years away. Red dwarfs are cool, stable stars that can maintain habitable zones much closer to their surface than our Sun. They're also the most abundant star type in the galaxy, meaning if life exists on planets like K2-18b, there could be billions of similar worlds out there. The planet itself orbits its star every 32.9 days, receiving roughly Earth-like amounts of stellar radiation. It's positioned right in the habitable zone, where the temperature should allow liquid water to exist on the surface. But here's what makes K2-18b truly revolutionary. Its mass is 8.6 times that of Earth. Its radius is 2.6 times larger. This makes it a world we've never encountered in our own solar system. Astronomers call it a super-Earth, or more recently, and more intriguingly, a hycean world. A hycean world is hypothetical. Scientists like Medhusudhan theorize it could be an entire planet covered in a global ocean of liquid water, with a thick hydrogen-rich atmosphere above it. Think of it not as Earth, but as the opposite. Instead of land with oceans, this is ocean with a sky. The implications are staggering. On Earth, life emerged in the ocean. The earliest organisms were aquatic. It took billions of years before life crawled onto land. If K2-18b is indeed a hycean world, its oceans could stretch for thousands of kilometers, unbroken and continuous, with a stable climate sustained by the thick atmosphere above. The average temperature, if our models are correct, would be temperate. Not Earth's 15 degrees Celsius, but somewhere in a range where water remains liquid, where chemistry could happen, where, potentially, life could persist. In 2023, astronomers made the first observations of K2-18b's atmosphere using the James Webb Space Telescope, the most powerful instrument ever built. What they found changed everything. Part 4. The Atmosphere Revelation, 2:45 minutes. Why this planet matters. When the James Webb Space Telescope analyzed K2-18b's atmosphere through infrared spectroscopy, it revealed a composition that no one expected on a sub-Neptune world. Methane, carbon dioxide, and something else, a molecule with profound implications, dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine microorganisms. Phytoplankton, algae, living things that generate this gas as a byproduct of their metabolism. The detection sent shockwaves through the scientific community. For decades, scientists have theorized about biosignatures, detectable signs of life. For the first time, we had potentially detected one on a distant world. But the science is complex. DMS can be produced through non-biological processes. High-energy radiation striking organic molecules can create the compound without any life present. And the detection itself is tentative. It appeared at what scientists call 2.7 sigma confidence, which is below the 5 sigma threshold required for a conclusive discovery in astronomy. Still, the atmospheric composition as a whole paints a stunning picture. A world with water, carbon, hydrogen, the building blocks of chemistry and potentially of life. The presence of these molecules in the same atmosphere, in concentrations that match our models of a habitable ocean world, is difficult to explain without invoking biological processes. Think about it. We've spent the entirety of human history wondering if life exists anywhere else. And now, for the first time, we have a world that possesses not just one habitable characteristic, but several in combination. A world whose very atmospheric composition raises the possibility of biology. The scientific establishment was transfixed. Papers were published. Debates raged about the significance of these findings. And then, in 2026, the community decided it was time to search directly for signs of technology. Part 5. The SETI scan, 2:20 minutes. The search begins in July 2026, just weeks ago. Astronomers pointed two of the most powerful radio telescopes on Earth at K2-18b. The Very Large Array in New Mexico. The Meerkat Radio Telescope in South Africa. Combined, these instruments can detect whisper-quiet radio signals from unimaginable distances. For 33 days, the length of one K2-18b year, the telescopes listened. They scanned for narrowband radio signals, the kind that would indicate technological broadcasting, not natural cosmic radio emissions, not stellar noise, but the unmistakable signature of engineering. Transmitters, communication systems, proof of a technological civilization. Millions of candidate signals were identified during the observation. Every one was examined, classified, and analyzed. Scientists looked for patterns, for deliberate structure, for anything that suggested intelligent design. And they found nothing. No signals consistent with Earth-like technology. No obvious narrowband transmissions. No smoking gun indicating an alien civilization broadcasting to the cosmos from K2-18b's surface. The result was, simultaneously, disappointing and profoundly informative. It told us that if there is life on K2-18b, it either hasn't developed radio technology, doesn't transmit in the frequencies we searched, or employs methods so different from our own that our instruments cannot detect them. But here's the crucial point. This search did not rule out life on K2-18b. It only ruled out Earth-like technological civilization using Earth-like radio methods. Biological life, microorganisms, perhaps, or even complex ecosystems, could exist on that world in profound abundance without ever broadcasting a single radio wave. Life and technology are not synonymous. Intelligence and radio transmission are not prerequisites for one another. The search revealed something else too. It demonstrated that we are finally capable of performing this kind of science. We can study distant worlds in detail. We can search for technology across interstellar distances. The tools exist. The methodology is sound. The era of the search for extraterrestrial intelligence has moved from theory to practice. Part 6. The Unexpected Discoveries. 2:15 minutes. Recent breakthroughs as scientists continue analyzing data from K2-18b. Unexpected discoveries keep emerging. First, the atmosphere is far richer in water than previously thought. Models now suggest water makes up nearly half of K2-18b's atmospheric mass. This isn't a planet with oceans beneath a thin air layer. This could be a world where water exists in all its phases. Liquid oceans, water ice clouds, perhaps even supercritical water near the surface. Second, the planet's mass suggests it may have a rocky core, not a gas giant composition as initially theorized. A rocky core means potential geological processes. Volcanism, mineral chemistry, the dynamic geology that, on Earth, drives the hydrological cycle and supports life. Third, recent analyses propose that K2-18b might host large moons, similar to how Jupiter and Saturn host dozens of satellites. These moons could create tidal forces that stir the oceans, drive geochemistry, and potentially support life in moon-orbiting systems. We might be looking not at one world with life, but multiple worlds in a single system. Fourth, and perhaps most intriguingly, K2-18b has a companion planet. K2-18c orbits the same star at a different distance. This binary planetary configuration creates gravitational interactions that could have shaped K2-18b's climate and habitability over billions of years. Each of these discoveries opens new questions. Each one makes K2-18b more complex, more interesting, more alien, yet paradoxically more similar to the dynamic worlds we study in our own solar system. Scientists also discovered that K2-18's red dwarf star, while small, is relatively stable. It doesn't have violent flares or extreme magnetic activity that would sterilize nearby planets. This is important. A world like K2-18b needs a stable star to maintain atmospheric chemistry and climate stability. K2-18 appears to provide exactly that. The picture emerging is not of a lifeless desert world or a toxic hellscape, but of a potentially habitable realm. A world of oceans under thick skies. A world where chemistry could become biology. Where, over billions of years, simple molecules could organize into living systems. Part 7. The worst-case scenarios. 2:00 minutes. Challenges to habitability, but K2-18b is not Earth. And the differences matter enormously. The first challenge, radiation. K2-18b orbits much closer to its star than Earth orbits the Sun. Despite the red dwarf being cool, the planet receives more stellar radiation. This could drive atmospheric loss, stripping away water vapor and hydrogen into space. A process that could render even a world with billions of years of water susceptible to gradual dehydration. The second, tidal locking. Some models suggest that K2-18b might be tidally locked, always showing the same face to its star, like Earth's moon always shows the same face to us. If true, one hemisphere would be eternally day, the other eternally night. Extreme temperatures and weather patterns. a planetary climate that seems incompatible with life as we know it. But here's the twist. Tidal locking can also create stable zones at the terminator, the boundary between day and night, where conditions might be surprisingly habitable. The third, extreme pressure. If K2-18b is indeed a hycean world with hundreds of kilometers of ocean, the pressure at the planet's surface could be crushing. Thousands of times Earth's atmospheric pressure. This creates conditions we barely understand. But life on Earth exists in Earth's deepest oceans, under extreme pressures, in complete darkness. We are only beginning to understand how life adapts to extreme environments. The fourth, stellar flares. Red dwarfs, while generally stable, can experience explosive flares, sudden bursts of energy and radiation. These events could devastate the upper atmosphere, cause mass extinction, reset planetary evolution. Life on K2-18b would need resilience, genetic variability, rapid reproduction to survive such catastrophes. The fifth, unknown chemistry. K2-18b's thick hydrogen-rich atmosphere, its exotic water-dominated composition, its potential supercritical water zones. These represent planetary conditions fundamentally alien to Earth. The chemistry that plays out under these conditions might prohibit the organic compounds that lead to life, or it might enable completely different biochemistry that we've never imagined. Each of these challenges is real. Each one makes K2-18b less hospitable than Earth. But each one also represents an extreme environment that life on our own planet has learned to navigate. In the deepest trenches, under Antarctic ice, in boiling hot springs, life finds a way. The question is not whether conditions on K2-18b perfectly match Earth. They don't, and they never will. The question is whether they're good enough for the incredible adaptability of life itself. Part 8. The Unsolved Mysteries. 230 minutes. What science still cannot explain despite the James Webb observations, the SETI scan, and years of modeling, fundamental questions about K2-18b remain unsolved. The first mystery, is the DMS signal real? The detection remains tentative. 3 independent teams of astronomers have examined the data and reached different conclusions about whether DMS is truly present in K2-18b's atmosphere or whether it's an artifact of the analysis process. The original discoverers stand by their work. The skeptics demand stronger evidence. The scientific method is playing out in real time, and no consensus has emerged. The second mystery, what is K2-18b's internal structure? We know its mass and size. We can model its gravity. But without a direct mission to the planet, a probe that could descend through the atmosphere and measure conditions, we're making educated guesses. Does it have a thin rocky core surrounded by deep oceans? A massive core with a thin water layer? Exotic ice forms that exist only under extreme pressure? We don't know. The third mystery, what is the origin of K2-18b's atmosphere? How did a sub-Neptune world retain such a thick hydrogen envelope? Most planets of this size, at this distance from their stars, should lose their atmospheres over billions of years. K2-18b hasn't. Why? Did the star become hotter after the planet formed, forcing atmospheric loss that stopped short of complete stripping? Did the planet form further out and migrate inward, its atmosphere densifying? The answer will tell us fundamental truths about planetary formation. The fourth mystery, could K2-18b harbor non-biological explanations for the atmospheric composition we observe? A network of chemically producing minerals on the ocean floor? A non-biological photochemical process we've never witnessed? Repeated volcanic outgassing over geological time? Scientists must consider every alternative before concluding that life is the best explanation. The fifth mystery, if life exists on K2-18b, what would it look like? Not what would it be evolutionarily. That's unknowable without direct observation, but functionally. Would it metabolize the way Earth life does, using water as a medium and carbon-based chemistry? Would it exploit K2-18b's unique environments in ways we couldn't predict? Would it be microbial, colonial, intelligent? These mysteries drive science forward. They motivate telescopes, satellites, and research budgets. They push humanity to ask harder questions and build better tools. Part 9. The Future of Exploration. 240 minutes. What's coming next? K2-18b story is far from over. In fact, we're at the beginning of a new era of exoplanet science. In 2027, the Habitable Worlds Observatory, a NASA mission designed specifically to study Earth-sized planets, will be deployed. It will have capabilities beyond even the James Webb Space Telescope, specifically optimized for detecting biosignatures in exoplanet atmospheres. K2-18b will be one of its primary targets. But direct observation from afar only tells us so much. The next frontier is exploration. Several space agencies are